In this video, I have with me a few questions related to electric field, which is from the standard 12th higher secondary course, and we are going to discuss those questions, and I'm going to provide you with the solutions. I hope they are correct. We have the answers of those questions, the direct answers. I'll just be providing you with the procedure to do that, and we'll see. So to begin with, we have this kind of a set. So this is the first one that we'll be dealing with, where we have been provided with the electric field intensity at a distance. That is the question number 26. Then we'll be moving over right up to question number 42. I hope to complete all of that in this single video, so I'll be pretty fast with my approach. You'll have to consider that. So to begin with, the first one that we have is to calculate the electric field intensity at a distance of 10 raised to the power minus 9 from a helium nucleus. Now, as far as the helium nucleus is concerned, so this is the answer number 26 that we'll be trying. So for the helium nucleus, which has 2 protons in it, so for 2 protons in the helium nucleus, we have the total charge to be equal to 2e, which is equal to 2 times of 1.6 times of 10 raised to the power minus 19 coulomb. This is the amount of charge that is there. And as far as the distance is concerned, we have 10 raised to the power minus 9. So the electric field, as far as the equation is concerned, we are just concerned about the magnitude as of now. So we have k q times divided by square of the distance. So k is 9 times of 10 raised to the power 9, as you know it, and q is 2 times of 1.6 times of 10 raised to the power minus 19, entirely divided with 10 to the power minus 9 squared. So that results in a value of 9 times of 2 times of 1.6 will give me 3.2 times, or 18 times of 1.6. So that's 256 plus 32. So that's going to be nearly about 28.8. And as far as the power of 10 is concerned, we have 10 raised to the power minus 10 in the numerator and 10 raised to the power minus 19, which minus 18, which goes up and becomes positive. So we have 10 raised to the power plus 8 at the end. We can keep it as 2.88 times of 10 raised to the power 9, and the unit being Newton per coulomb. So that's the answer for the first question that we have, which is exactly the same that we have obtained. Now, as far as the second question is concerned, we have the 27th one, which is 5 microcoulomb charge experiences a certain force of 1 millinewton in an electric field. So what is the magnitude of the electric field intensity at the position of the charge? So we know the relation. So we have the data that we have at hand is that the force being 5, the charge being 5 microcoulomb and the force being 1 millinewton. So for the 27th bit, we have force to be 1 millinewton. One is it? Yes, 1 millinewton, and then the charge being equal to 5 microcoulomb. So we wish to determine the electric field. Now the electric field we know is F over Q. So that is equal to, because F is equal to Q times of E. So electric field, we are only dealing with the magnitude as of now. So we have the value of F, that is 10 raised to the power minus 3 for milli, and 5 times of 10 raised to the power minus 6 for micro. And the value that we obtain from this is 1 over 5 is 0.2, and then we have 10 raised to the power 3 Newton per coulomb, or that is equal to 200 Newton per coulomb. That is the value of the electric field that we have. That is exactly what we have obtained as the answer. Now for the third bit, we have 2 charges 16 and minus 9 microcoulomb, which are placed at a distance of 0.08 meters apart in air. Now we want to determine the position of the point where the resultant electric field is 0. So let's check. So let's check the values of the charges, 16 and minus 9 and 0.08 distance. So the 28th one, we'll use a diagram over here. So this is 16 microcoulomb, and then there is minus 9 microcoulomb, and they are separated by a distance of what was that distance? Well, the distance was 0.08, I guess. Yes, the distance was 0.08. So 0.08 being the distance in meters, and we wish to determine a point where the electric field intensity will be 0. Now, the electric field intensity, usually when we calculate the electric field intensity, we consider a positive test charge at that point. Now, if we place a positive test charge in the middle, somewhere there, somewhere between them, then it will be repelled by that positive 16 microcoulomb, and it will be attracted by the minus 9 microcoulomb, and as a result of that, both those forces will be acting towards the negative charge, because negative charge will be attracting it while positive charge will be repelling it. So that won't really balance that field at that point. So what we need is, in order to balance things, we need an equal and opposite amount of vector, which in this case is the electric field, of course. So either we place it on the left hand side where the 16 is pushing it while minus 9 is attracting it, but on the left hand side it will be closer to the 16 microcoulomb charge, and it will experience a greater repulsion, while 9 having a less magnitude will, and greater distance, of course, because you can see the distance over there will be much greater, so as compared to that 16 distance. So with that, it won't really help balancing the electric field. So what we need is, we need a point which will be closer to this minus 9, because minus 9 has lesser magnitude, so obviously it will impact a lesser distance. So this distance, let that be, let us say that is x. So this distance from the positive charge that is over there, the distance is going to be 0.08 plus x. So that is probably the point where the electric field will be balanced, because the electric field due to the positive 16 coulomb will be along that direction, and with 16 being greater than 9, so obviously it can impact a greater distance, and then for minus 9 it will be attracted towards this direction, so it will even out, it will balance. So from that, what we get is, we put down the formula, the resultant electric field, if you write it in vector notation, what you get is, this is simply let me write E16 for the electric field due to 16, and then E9 for the 9 microcoulomb charge. And vectorially, if we are to calculate the magnitude of it, then we have E16 squared plus E9 squared plus 2 times of E16 times of E9 cosine of the angle. Now the angle, with the forces being equal, being opposite, the angle between them is going to be 180 degrees. So this is cosine of 180, and then we take the entire root over of that. Now I'm doing this because we are doing an initial part of it. I won't be repeating these steps in the further questions that have forces or vectors aligned in the same direction or same line or in opposite senses. This is just to show on the first occasion. So cosine of 180, as we know it, is minus 1, and we put that value over there. So this is E16 squared plus E9 squared minus 2E16 times of E9 entirely under root. So this is E16 minus E9 whole squared under root, and that is nothing but E16 minus E9 directly. So what is the value of E16? Now E16, as far as the magnitude is concerned, we have the value as K 16 microcoulomb divided by the distance, in that case is 0.08 plus x whole squared. And as for E9, we are having the magnitude to be equal to, now we know the direction, they are opposite of course, so we need not write that again and again. and here the distance being x squared. So now if we are to consider this, that the resultant has to be 0, because they will balance out each other, they will even out each other, and there will be no net electric field because the net electric field has to be 0. So that means what we are getting is, from this we are getting that E16 has to be equal to E9. So we equate these two that we have at hand. So that is E16 is equal to E9. I put the values over there. So this is K16 microcoulomb divided by 0.08 plus x, and this is K9 microcoulomb divided by x squared. The K and the micro terms get cancelled out. This is square, of course. And then what we have is we can take the ratio. So this is x over 0.08 plus x completely squared, and then we have on the other side we have 9 over 16, just a cross multiplication. Now if we take the root over of that, then we end up with 3 over 4. So then we cross multiply again, so we have 4x, 4 multiplies with the x, and then we have 0.08 times of 3, which is 0.24 plus 3x. So 3x goes to the other side, and we are just left with x only, because 4x minus 3x, so I cancel it out like that. Don't get confused. So x is simply equal to 0.24. That is the value that we obtain. X is equal to 0.24 meters. So it will be at a distance of 0.2 meters from the -9 microcoulomb charge that is provided to us. So that is exactly the answer that we have obtained, and this is the procedure in which we are trying to obtain the answer. Okay, so let's go to the next part, question number 29. It may not be clear, the image that I have for you, but at least because this is a image file which I've converted to PDF to show you. So the 29th question has the charges 15, minus 15, 20 and minus 15 to be placed in order at the corners of a square of side 0.2 meters. We need to calculate the electric field intensity at the intersection of the diagonals. So 15, minus 15, 20 and minus 50. And what do we have there? We have the sides to be equal to 0.2 meters. So let me draw the image for you for that. So this is the image or the figure related to the question, where we have 15, minus 15, 20 and minus 50 going in that cyclic order, with the at the vertices of a square of each side 0.2, and we wish to determine the electric field intensity, the net electric field intensity at the center of that arrangement. Now in order to proceed to such a question, what we first of all do is we erase this first of all, because that's going to disturb us. We want to determine the net electric field there, so we know that. So we'll see how I'll do it. Now as you know, the diagonals intersect each other at 90 degrees. So with all those charges available, first of all we need to imagine a positive test charge right at the point where we wish to determine the electric field. So that is over here at the center. Now the 15 microcoulomb, let's start from that corner. So 15 plus 15 microcoulomb, that will push that positive charge along that line. So this is, let's say this is E15. I write it as E15. It will be along that line. And then the 20 microcoulomb that we have, again that is a positive charge, so that will push the positive charge that is probably placed at the point of intersection, and it will be E20 along that line. Now from the previous question that you have just observed, if two vectors they are opposite to each other along the same line, then we have a resultant which is the higher value minus the lower value. So in this case 20 for that same distance, because the point of intersection will be at the same distance from both those charges. So for the same distance of that central point, E20 will have a greater impact than E15. And by what magnitude? Obviously the magnitude will be 5, because 20 minus 15 is 5. What you are going to end up as K, the electric field due to 20, we are just considering the magnitude over here, K 20 micro divided by, let's say the distance over here is d, it will be d for each of those cases, divided by d squared. And then we have for E15, we'll have the value to be equal to K 15 micro divided by d squared. Now as for the resultant, in that case we'll have E20 minus E15. Remember, because we are considering the magnitude over here, so I'm taking the negative of one of the vectors. Had I kept that in vectors, then I would have done the vector addition, which would have resulted in the subtraction of those magnitudes. So that is equal to, if you take note of that, K over d square is the same, but 20 minus 15 will be simply 5, and we can keep the micro as common term. So what we are getting, I'm drawing this separately over here. So what we are getting is, at the center, let's take that point as O. So from that point O that we have over there, we'll have an excess of E, let's say E5. We are getting E5 over here. I take it as E5. Similarly, on the similar line of explanation, we have 50 microcoulomb in negative and 15 microcoulomb in negative, exactly opposite and at same distances. This is also D, this is also D, because the diagonals, half of the diagonal as well as the diagonal themselves, they will be the same. So in that case, if a positive charge is placed at that point O, it will be attracted by this negative minus 50. So this will be E50 along this direction, and E15 will be along that direction. This is not E15, but this is E minus 15, because this is E15 already I have written over there. You may get confused. So the resultant in that case will be, because this is 50 and this is 15 in negative, of course, so this is minus 50. So E minus 50 minus E minus 15, they will be exactly acting in opposite directions, and if you can guess it correctly, you will have K over d square. This will be 35 micro, and the resultant will be obviously directed towards the minus 50, because that has a greater magnitude. So I can obviously, this is not to scale, but this is somewhere, I take it as E35. So this is E35 along this direction. E35 and E5 are the two resultants that we are getting because of that, because of those four charges. So now if I am considering the angle between them, obviously the diagonals bisect or intersect each other at 90 degrees. And so the resultant in this case will be, the net field that we were supposed to obtain is actually the resultant of these two vectors, and these two being in 90 degrees. So we have E35 squared plus E5 squared under root, because cosine of 90 is going to be 0. So a square plus b square plus 2ab cos theta, or 2 cos 90. Cos 90 is going to be 0. So we are leaving that out. So this is equal to E35 that we have obtained. All of those terms are having K over d square. So K over d square can be taken out. We'll put those values later. And then over here, and also the micro term that is going to be common in both the cases, square of that and root over of that, we are going to get all of that outside the square root. So we have 35 squared plus 5 squared in this case, and now we are going to put those values over there. So this is K 9 into 10 to the power 9. For micro we have 10 raised to the power minus 6. For D, because this is 0.2, so this is the distance D is going to be half of the diagonal. The diagonal is a root over of 2 times of A, that is the side, and divided by 2. So A over root 2, that means 0.2 over root 2 squared. I can take that root 2 squared over here, and what is left under root is this is 35 squared is 1225, and 5 squared is 25, so this is 1250. 1250 is actually 25 root 2, because 625 times of 2, so that is going to be that. And then we have 4 times of 10 raised to the power minus 2 over here, 10 raised to the power minus 6, 10 to the power 9, and a 9. If you equate or calculate that out, what you are going to get is simply 1.59, the value, times of 10 raised to the power 7 coulomb, Newton per coulomb, beg your pardon, Newton per coulomb. So that's going to be the value of the net electric field. But I'm also going to provide you with the direction that is involved. Now, because this E35 will have a greater impact on that resultant, so considering the parallelogram law of vector addition, we can say that this is going to be along this direction. This is the resultant E net. And let us say that it is making an angle alpha with respect to E35. So in that case, as we know from the case of direction of the resultant, we have tan alpha to be equal to, tan alpha will simply be equal to E35, because this is 90 degrees, so obviously we are having E5 over E35, because this is E5 and this is E35. So E5 and E35, the ratio of that, this is the perpendicular and this is the base, so that is tan alpha, and that is equal to, well, if you have the values over here, you can compare that. Only thing that remains is 5 over 35, which is nearly 1 over 7, which is nearly 0.14. So alpha is going to be tangent inverse of 0.14. That's going to be the direction if at all it has asked. But if you are only concerned about the magnitude, you have this value. But in case you are asked for the direction, you can obtain that as well, which is pretty easy in this case, given the angle between the two vectors is 90 degrees. Now in the 30th bit, we have an oil drop of mass 1 milligram having a charge of 2 10 to the power minus 6 is micro, so 2 microcoulomb, suspended in a box. Obviously it is suspended by an external magnetic field which is balancing it. So what is the magnitude of that electric field that is actually balancing it? So let's try that. So the data that we have at hand is 1 milligram of mass and the charge being 2 microcoulomb, and that is balanced. So for the 30th bit, we have an oil drop, basically spherical, and it would have fallen down considering the weight, but that oil drop carries a charge of 1 microcoulomb, not 1 microcoulomb, it's probably 2 microcoulomb. So this is 2 microcoulomb, which means it is positive, because had it been negative we would have had a minus sign over there. And obviously there will be an electric field which will be repelling this positive charge in that direction, that is the F electrostatic force, which will be going in the upward direction, which will be balancing its weight, and that is how it will be suspended. So what is that value of that electric field which is applying such a force, which is balancing its mass, the mass balancing its weight actually, so that it remains suspended. Now the mass that has been provided is 1 milligram. So as far as the equations are concerned, we have the charge times of the electric field to be equal to the electrostatic force, and we have the weight to be equal to mass times of the gravity, acceleration due to gravity. Now the mass that is provided is, this is 1 milligram, not G does not stand for gravity over here, so this is for the mass. I'm writing it as capital M. So then we have, in order that this is balanced, Fe is equal to W, then we have Fe to be equal to 2 microcoulomb times of the electric field, which is to be determined. And then as for the weight, we have 1 milligrams, which is 10 raised to the power minus 3 grams, then we have to convert that in kgs, so in SI system. So that means it will be further from grams. It will be, let me strike that out, grams. It will be 10 raised to the power minus 3 for grams, then 10 to the power minus 3 for kg. So this will be this many kgs. That is 1 micro times of that. This is 1 micro kg. And then we have 9.8 as the value of g. The micro gets cancelled out on both sides. We have just a value of 2. E is therefore equal to 9.8 over 2. So that's pretty simple, 4.9 Newton per coulomb. In case you didn't understand about that 10 raised to the power minus 3 and 10 raised to the power minus 3, I can write it over there. That is 1 milligram is equal to 10 to the power minus 3 grams, but we have to convert that in kg. So 1 gram is 10 raised to the power minus 3 kg. So that is exactly what I've done over there. There shouldn't be any confusion. Now moving over to the 31st question, which is asked us to calculate the magnitude and direction of the electric field which keeps the proton just floating. The mass of the proton has been provided as well as the charge. So the magnitude and the direction of the field, it's exactly same as that of the previous one, where the field was acting in the upward direction to balance a positive charge. So I won't be really doing this uh, because as you know, the procedure is exactly the same as the previous one. So I would really request you to try it yourself, so that to check whether you have understood the discussion that I did for the previous question. Then the next one has the 32nd bit, that is the charged particle. A charged particle of mass 1 gram is suspended through a silk thread of 0.4 meters in a horizontal electric field of 4 times of 10 raised to the power 4 Newton per coulomb. So if the particle stays at a distance of 0.24 meters from the wall in equilibrium, find the charge on the particle. So now this is a question of balancing vectors. It's the same way, but only thing is that instead of the vertical field that we used in the previous two questions, there's a horizontal field over here, and the particle is suspended from a silk thread of a certain length. So let me provide you with the figure first, so that you are clear about what has been asked. So this is the case given over there, that a positive charge is provided to a certain particle which is suspended from a silk thread being light, so we are not going to consider that mass, and it is of length 0.4 meters, so from that wall or that rigid support at the top. Now the electric field that is provided is in the horizontal line, so obviously what that will do is it will push this charge along this direction, and what happens in that case is that this thread is going to be suspended like this in a slanting way, making a certain angle probably. Now instead of the 0.4 that we had over here, now the distance has reduced to 0.24 meters. That is exactly what it has said. Now with the mass being 0.1 grams, 0.1 or probably 1 gram, no, it's 1 gram. So with the mass being 1 gram, we want to determine the charge that is there, so that it remains balanced in that oblique sense, in that slanting way. So let's see what are the forces that are involved in it by considering the free body diagram. Now the string, so let me draw the particle once again. So this is the particle. It is experiencing an electrostatic force of repulsion from the field along this direction, and it is experiencing a tension, the tension along the string, that is along the silk thread, along that direction. And if this angle over here is theta, then obviously the vertical line, from that vertical line it will be making an angle theta as well. So this is theta, interior alternate angles, and then the weight is going to act along this direction, and so we have the tangent, the cosine of the tension, the cosine component, that is the horizontal component of the tension, to be balancing the weight, while the sine component of the tension to be balancing the electrostatic force of repulsion, and as a result of that it is staying in its place. Now, because the distances have been provided, it will be easier. We have already discussed about the balancing conditions that we have. The vertical force that we are considering in this case, that is mg, that gets divided by the vertical distance, that is equal to 0.24 now, because with the reduced distance, this is the new distance. What we are concerned about, we will be determining this distance, that is the horizontal distance from the initial point. Now this distance over here will simply be equal to 0.4, which is now the slanting distance, 0.4 squared, that is the hypotenuse, minus 0.24 squared. We can take it as 40 minus 24. 40 is 1600 and 24 is 576. So this is 1600 minus 576, which approximately results to 1024. So this is going to be 0.1024 probably, and 1024 is the square of 32. So what we are going to get is, this is approximately 0.32, not approximately but exactly. So now that horizontal distance is 0.32, so this is vertical force by vertical distance, and that will be equal to the horizontal force, that is the electrostatic force of repulsion, divided by the horizontal distance, that is 0.32. 0.24 is cancels out with 0.32, because all of them are divisible by 0.4. So this is actually going 6 times, and this is actually going 8 times. So we have 6 and 8 again is 3 and 4. So we have Fe over mg to be equal to 4 over 3. And as far as Fe is concerned, there's a charge and there's an electric field. So the electric field is 4 times of 10 raised to the power 4 divided by mg. M is 1 gram, which is equal to 10 raised to the power minus 3 kgs. And then for g we put the value as 9.8, and then we have 4 over 3 over here. So the 4 cancels out, so 1 remains in that case. So now we have the value of charge to be equal to, well, 9.8, 10 raised to the power minus 3 can go up, and then we have 3 times of 10 raised to the power 4, that comes down. So 9.8 over 3 is approximately 3. Well, it would have been 3.3 had that been 9.9. So this is 3.267, I guess. I don't know. You can check that for yourself. 32, yes, probably that. And then this is 10 raised to the power minus 7 coulomb. But as I checked it, that is probably not the answer. The answer that has been given is 1.838 times of 10 raised to the power minus 7. The reason why we have obtained that answer is because I have considered the wall as the top wall. What it had meant in the question, so this is probably my mistake on applying the conditions. So what it has said is that the distance, the horizontal distance, is 0.24 instead of this distance. So with that length of the thread, obviously now that we have calculated out the other one, so this is going to be 0.32. So that means these two things will be swapped over here. 0.24 will go that side, 0.32 will come this side. So that means the balancing equations will be mg over 0.32 and then we have Fe over 0.24, and as a result of that we have Fe over mg to be equal to well, now this is 3 over 4 instead of 4 over 3. So in that case we'll have 0 this is 4 times of 10 raised to the power plus 4 into q divided by 10 to the power minus 3 times of 9.8. The same procedure. The thing is that the wall obviously was this one and the rigid support was there. Of course the wall is this sideways, what I had considered is the wall at the top. So never mind, we still have the answer for both the processes if you take it in the positive sense, and that divided by 4 times of 10 raised to the power 4, and 3 times of 9.8 is approximately coming out to be 29.4, and 29.4 divided by 16, if you check that, then it comes out to be that value, that is 1.838. And obviously 10 to the power minus 3, 10 to the power minus 4, when that goes to the top is 10 to the power minus 7, and that is coulomb. So this is the answer that we were looking for, considering the wall stays over here rather than the top one that we have considered over there. So be careful about the wall, where it is exactly. Then in the next bit, that is the 33rd one, we have to determine the number of electrons that must be removed from a coin of a given mass, that is 1.6 grams, so that it floats in an electric field intensity of 10 raised to the power 5. Is it? It's probably 10 raised to the power 9. It's not clear. So it's 10 raised to the power 9 Newton per coulomb directed in the upward direction. Now this again is in the similar line as that of 31 and 32, where you have an upward electric field balancing the mass or the weight. Now electrons removed, that means it will carry a positive charge. Now you have to determine that charge, and from that charge you'll have to use the quantization concept. So let's see. So you have that coin of the mass, that is 1.6 grams, and the weight acting in the downward direction. That weight is balanced by the electric field, so you have the force. Now the force is equal to Q times of E, and that will be balancing the weight. But as far as Q times of E is concerned, you have the quantization, that is N times of E in that Q, and that multiplied to E is equal to mg. So all you need to know is En, that has been asked, the number of electrons that need to be removed in order that this remains balanced. So this is m times of g divided by E times of E. So m in this case being 1.6 grams, which is 1.6 times of 10 raised to the power minus 3 kgs, and then as far as the gravitational value is concerned, that is 9.8, and this is 1.6 times of 10 raised to the power minus 19 for the charge of an electron or a proton, maybe the value of E, and the electric field that is provided is 10 to the power 9. So this is 10 to the power minus 10, and that goes up, so that's plus 10, so 10 raised to the power 7, 1.6 cancels out, so 9.8 times of 10 raised to the power 7 is the number of electrons that are removed so as to obtain that balancing condition. Then in the 34th bit, we have 2 point charges 20 and 80 microcoulomb to be all positive, to be separated by a distance of 0.18 meters, and the position of the point where the electric field is going to be 0. This is exactly in the same line as that of the question that we have tried earlier, probably the 28th or 29th one. So let's see what we have over here. Difference with this being that it is carrying positive charge instead of the positive and negative charge. So over here you have supposedly 20 microcoulomb, and this is 80 microcoulomb. Now had this been positive or negative, you would have obtained the balancing point on either side of this arrangement, but because both are positive, and same would have been the case for both negative, we would have obtained the the electric field, we will be obtaining the electric field between those two charges. Now, the electric field between those charges, with the electric field being zero, it will be obviously closer to the charge having lesser value than the charge having greater value, and the total distance being here equal to 0. If I remember correctly, 18 meters probably, then this will be of 0.18 minus x from the 80 microcoulomb. And if we are to consider the case of the electric field being zero at this point, then the net field will be zero when the electric fields will be balancing. Now that we have done this earlier, so I'll be writing the formula directly. K and micro, all of that will cancel out, but let me write that for you once again. So this is x squared, and this is k times of 80 micro over 0.18 minus x whole squared. And if we cancel out these terms, 20 goes 4 times in 80, and then we have 0.18 minus x over x entirely squared to be equal to 4. You take the root of that, you get 2. So you have 0.18 minus x is equal to 2x, so 3x will be equal to 0.18. So we have x to be equal to 0.18 over 3, and that is going to be equal to 0.06. So 0.06 meters from the given 20 microcoulomb charge is where the electric field is going to be 0, or we can say 0.12 meter from the given 80 microcoulomb charge where the electric field is going to be 0. So what we must remember in these cases, let me just give you a point analysis over it, that if we have a positive and a negative charge of different values, of course, and we have the value of the positive, let's say the positive charge is having a greater magnitude as that of the negative charge, then the balancing point is going to be near the negative charge on the other side, because this is having a lesser magnitude, so obviously it will impact in a lesser sense than that of the positive charge. Now, so there you have to add that distance when we are considering this distance. Let us say the distance of separation is L over there. So the balancing condition will be Q over L plus X whole squared, and that is equal to Q prime over X squared. Now this is the first condition. The second condition being that we are considering the case of, so this one's for this, and let's say Q is less than Q prime. That means the positive charge has a lesser value than the primed charge, that is -1. So the balancing point will be near this. Let's take it as let's have this as x prime. So in that case, you will have the balancing condition to be equal to Q over x primed square to be equal to Q prime over L plus x prime square. So that's the case over here. And then if we are having two positive charges and or we are having two negative charges, let's say, then in both those cases you are going to have the balancing point at the center. Let's take this distance as x, or this distance as x primed, and the total length being equal to L between the two charges, the distance of separation, that is. So in each of those cases, what you are going to end up as, you are having k over x squared is to be equal to, not k, q, and q prime over L minus x whole square. Then over for this case, you are going to have q over x prime squared. And remember, the distance here, it is immaterial whether the charge is having lesser or greater, because as it is that you are going to end up at the correct place. But here it is very important to choose the side, whether you choose this side or this side, depending on which charge has a lesser magnitude. Here you will eventually end up to a distance which is closer to the lesser magnitude, of course. So there's no problem with this one when we are considering the middle, but when we are considering the either side, at that time that becomes important to choose which side we must consider. For the next one, that is the 35th one, we have again an arrangement of four charges at the four vertices: minus 2q plus 2q minus q plus q, taken in that cyclic order, and that length of each side being equal to 0.02 meters. We wish to determine the electric field intensity exactly at the center, that is the intersection of the diagonals, and is given that each charge, that is q, that is the q factor that is there, that q is equal to 0.02 microcoulomb. Now, that's the value that has been given for the charge, each charge minus 2 plus 2 minus q plus q. So we take this and we obtain the electric field intensity at the center. We have done this for that uh, 50 15 15 50 50 15 20 50, that one, that is. So now we are having this value, so let's check. So this is the arrangement. We have just been given that the value of q in each case is 0.02 microcoulomb. Now, with the information that is available, the negative charges will be attracting any positive test charge which will be placed at the center, and obviously minus 2q will be having a greater magnitude as compared to this minus q, which is lying exactly opposite. So the resultant will be the E minus q, the excess charge in that direction, as we have done earlier. And then we have the case of, let me erase that for clarity, I'll be drawing it somewhere else. Let's take it over here. So this is from the point O, this is going to be E minus q, because that's only the excess charge that is offered by this as compared to the negative charge over here. And then for this 2q, which will be which is greater than the q that is there, so we will be having E plus q in this direction. Now, as you may also see that both those resultant vectors, that is E minus q and E plus q, they'll be having an exactly equal magnitude, and with two vectors having equal magnitude, you will have the resultant to be exactly bisecting those two vectors. This is the net electric field that we are going to get, and this will be exactly in the left hand side. So from that point over there, this is going to be parallel to both those upper and lower sides, and it will be exactly along that direction. Now, only thing is that we have to determine the net field. Now, the angle obviously is going to be 90 degrees, so it is going to bisect that, so 45 45 each. What we want to obtain is that E minus q or E plus q, you take the magnitude of either of them, that's going to be the same. So let's take for E plus q, which is equal to kq over, let's take this as d. So k is 9 times of 10 raised to the power 9, q is, as we know it, as 0.02 times of 10 to the power minus 6, and then we have the distance over here to be equal to 0.02 squared over root 2 squared. So that means there is a 2 factor which is going to come over here, and then we'll have 0.02 squared is simply 4 times of 10 raised to the power minus 4 in that case. So these this all of this value that you are going to get in this is going to give you 9. The 4 is going to cancel out with one of them, so 9 times of 10 raised to the power 4 and 5. Okay, so this is 9 times of 10 raised to the power 5 Newton per coulomb. So this is the value of this as well as this, because both have the same magnitude. Now, considering the angle being 45 degrees, you have cosine of 45 of E minus q and cosine of 45 of E plus q to be acting along the E net direction. So you have E net to be equal to 2 times of EQ, you take it as EQ or E minus q, cosine of 45, because EQ cos 45 plus EQ cos 45 is going to be 2 EQ cos 45. So that is going to give us, cos 45 is 1 over root 2, that cancels out with 2 to give us root 2. So this is 9 root 2 times of 10 raised to the power 5 Newton per Coulomb. So that is going to be our value for the net electric field in this arrangement. Now the next one, the 36th one, is exactly similar to the previous one, so I'm not going to try that. It has Q minus Q to be placed in that order with the side given as A. So you're going to get an expression as given below. So you can see that's the answer available to you, and you can try that yourself, and you can see for yourself that whether it's coming any close to that value or that expression. I'm sure you will get the answer because we have done this problem in the similar line as that of the 35th one. It is in that same line, so you're obviously going to get the result pretty efficiently if you have understood the previous one. So test yourself with this question. We'll, however, consider the next one, that is the 37th one, where we have a helium nucleus traveling at a speed of 10 raised to the power 7 times of 10 raised to the power 6 meters per second to be striking a gold film. This is the popular gold foil experiment, the scattering experiment by Rutherford. And by considering only the electrostatic repulsion, what is the closest possible distance of approach? So we wish to determine the distance of closest approach in this case. The only thing is that we have the value of the incident helium nucleus, that is 7 times of 10 raised to the power 6, and with the atomic number of gold as well as helium available to us. Let's try this. Let's first picturize this, then we can do this pretty easy. So in this case is the popular alpha particle scattering experiment. So what happens is that we have a helium nucleus. It's actually the alpha particle, and that is He2 plus, and because that has no electron, so that is approaching a gold film that is placed in front of it. And that gold film, obviously, let's assume that a highly exaggerated or magnified view of an atom of gold, the atomic number being 79 in this case. That means it has 79 protons, and this has 2 protons, because 2 plus, so helium is 2 protons, and this is 79 protons. Now what happens is that it is moving with a velocity which is equal to 2 times of 10 raised to the power 7, I guess that's the value. Oh, no, that's 7 times of 10 raised to the power 6 meters per second, if I'm not wrong. And with that speed, what happens is that this is a massive nucleus as compared to this one. This is a lighter one. It will approach to a distance which is closest, let's say that is d, and then it will come to rest at this point, and then it will be repelled along the same line. So first of all, moving at this speed, it will reduce to a speed that is 0. This is the final speed. This is probably the initial speed. So there will be a change in kinetic energy as it comes to rest. The change in kinetic energy is exactly equal to the kinetic energy that it had initially, because the final kinetic energy is obviously 0. And that change in kinetic energy is equal to the work that is done to take it to 0, which means is equal to the potential energy of the system, which is consisting of this system, that is 2 charges, one of 79 value and the other of value 2, that is of Z, and that system remains in a momentary equilibrium due to the repulsive force offered by the gold nucleus. So the change in kinetic energy is obviously equal to half m, if you are taking this as u, so let's take it as u squared. And what's there for m? Well, the mass of proton as well as neutron can be taken to be nearly equal just for calculation purpose, and it is 1.67 times of 10 raised to the power minus 27 kgs. And there are four of them because there are two protons and two neutrons. That is 2 and 2, they make 4 because this is He 24 that we write. So 4 here represents the mass number, which is obviously the number of nucleons in that case. And they are 4 in number, and their mass is nearly similar, 1.672 for proton, 1.675 or probably 48 for neutron, but we'll take it as 1.67 for just for easier calculation. And then we have the value of U, that is 7 times of 10 raised to the power 6 squared, and this is the change in kinetic energy. Now what happens here is that it is moving with a certain speed for sure, but this will be offering a repulsive force from this gold nucleus. Now that repulsive force, electrostatic repulsive force Fe, now as this is moving along this direction, that is the alpha particle, if it moves through a distance, let us say dx, with a force acting in this direction, that is the electrostatic force of repulsion, there'll be some work done, and that work done is equal to dw, small amount of work done, against for the motion of the alpha particle against the force that is offered by the force of repulsion offered by the gold nucleus. So that means this is F dot with dx, which is exactly in the opposite direction because the force is repulsive one. So this is cosine of 180 degrees. So that means this is minus 1. So this is minus f dx. Now it will be approaching from a very big distance as compared to this d that we are having over here. So that bigger distance as compared to that d can be taken as undefined or probably very big, that we can take it to infinity. So the total work done against this repulsive force by the moving or approaching helium nucleus, that gets stored in it in the form of potential energy. So this potential energy is actually the work done by the approaching alpha particle against the electrostatic force of repulsion. And so we are taking the integration for the total work as the integration of dw, that is the small work for the small displacement dx. So the total displacement here will be f times of dx, and the negative sign obviously stays out of the integration, and we are taking it from infinity to the point in consideration, that is d. Now we know the expression for the electrostatic force Fe, that is in each case this is Fe, electrostatic force. So that is equal to, in this case that is going to be equal to, as we know it, K, we'll take it as Q1 Q2 over well, let us say it was measured when it was at a distance supposedly x. So this is x squared times of dx. The dot is not there. Let me erase that. Let me create some confusion. So that is k q1 q2 over x squared times of dx, integrated from infinity to the closest approach, that is d, where it will stop and thereafter it will return along its path. So that is equal to, the minus stays as such, k q1 q2, they are all constant terms, and this is dx over x squared integrated from infinity to d, and that's going to give us minus of k q1 q2 and x raised to the power minus 2 plus 1, so this is minus 1, and the minus of this is from the formula for integration, the minus multiply to become plus, so k q1 q2, so this is 1 over d, the upper limit, minus 1 over infinity, the lower limit, that's going to go to 0 for sure. So we have k q1 q2 over d for this expression. Now This is the energy, the potential energy that is stored when work is done against the electric field that is offered by the heavier gold atom. And we have the charges, Q1, Q2. What is Q1 and Q2? So this potential energy is stored in the system due to this change in kinetic energy. So del Ke is going to be equal to U, and from that we can calculate the distance of closest approach. So this is, we are going to put these values over there. So this is half. Well, 1.67, if you calculate that, that's nearly 5 over 3, because 5 over 3, 6 over 3 is 2. 1.67 is nearly equal to 5 over 3. So keep that in mind if you are to calculate anything having a decimal factor of 0.67. You can always divide that, you can always take that as a fraction of 3. So that's easier in that way. And this is 4, this is 7 squared. We'll keep it as 7 squared in case it gets cancelled somewhere. And 10 raised to the power 12. As far as U is concerned, we have 9 times of 10 to the power 9 for K. Then you have the value of Q1, that is 79. 79, that is the atomic number of gold. And then you have 2 as the atomic number of helium. And you have the charge squared, because QE, 79E and 2E. So you have E squared over here, and that divided by D. So all of that, finally you obtain the value of D as follows. That is, well, there's a lot of cross multiplication to be done. So this is 9 times of 10 to the power 9, 79, 2, 1.6 times of 1.6 times of 10 raised to the power minus 38, if you check that out. And that, this 2 and 3 from the denominator, they go over here. That's a big one. And then you have 5, 10 raised to the power minus 27, 4, 7, 7, 10 raised to the power 12. Very long one. Now when you have such a messy calculation in front of you, it's ideal to consider the near or the closer numbers so that you can calculate them easily. See, you have, let me use another ink for you so that you can observe exactly what I'm trying to say. So you have a value of 79 over there, which is nearly 80. Considering the power terms of 10, it won't really matter if you take a simple 79 to 80. So we take it as 80 over here, which eventually cancels out with this 4 20 times. Then for that, again, this is 7 times of 7 is nearly 49, so this can be taken as nearly about 50. 50 is 100 over 2. So actually what I'm going to do is I'm going to take it as 100, and over 2 I'm going to put it over here. So that makes my calculation pretty easier. So now this is, we take this both, this is 10 to the power 14 actually. So now things look a bit simpler than the previous one. So what we have over here is that 9, we have a 2, I have a 2 from this. We take out all the zeros first to make things simpler, much more simpler. So this is 10 to the power 9. We have a 10 over here in 20. We have 1.6 and 1.6, so that's 10 to the power minus 2. So this is 10 to the power minus 40 if you take that 10 to the power minus 2 from them. So 10 to the power minus 40, 10 to the power minus 10 to the power 9, and 1 is 10. So 10 to the power minus 30. In the denominator, you have 10 to the power minus 27. You have 10 to the power 10 to the power plus 14. So this is 10 to the power minus 13. That's all the powers of 10. As far as the rest of the terms are concerned, 9 times of 2 times of 2. So that is 9 times of 4, 36. 1.6, 1.6 is 256. So 36, 256. And then we have 4 times of 3 is 12. and down below we have a 5. It's fairly easy as compared to the numbers that we were seeing right from the beginning. So I think this is achievable, this calculation. Let me make things easier for you, even easier. 256 can be taken nearly as 250, and 250 times of 4 is going to be 1000. 4 is in this term, that is 12, so even it's present in 36 as well. So you have 250 times of 4 is 1000, so you take that out of that 36, so 9, and then there is a 12, and then there is a 1000 over here, which comes out from the 256, and there's a 5 over here, so 5 again can be 10 over 2, so you take a 2 there. And as far as the powers of 10 are concerned, we have minus 17 now, and now it's fairly easy to calculate because you can cancel out one of those 10. So this is 10 to the power minus 15 now. 9 times of 12 is 108. 108 times of 2 is 216, nearly equal to 216 times of 10 raised to the power minus 15. So we can take it as 2.16 times of 10 raised to the power minus 13 is what I'm getting the distance. Well, this is in meters. You can check for yourself if it is correct. If it is incorrect, then probably you will have to consider those values accurately. Uh, this is my way of calculating things, so it's not it's to make things easier for you. You can take that route, or you can just calculate them directly. That's your option. Well, as you can see from the answer, it's 2.2 times of 10 raised to the power minus 13, so it's nearly 2.16. It might have rounded that off, but it's very effective when we are considering these kind of calculations. Okay, the last one from this page has half of the question in this page. That is, we have a certain metallic sphere of a certain volume that is given, that is of 10 raised to the power 6 meters squared, and 10 raised minus 6 meter cube, that is the volume, and that has a certain mass, that is 7.5 times of 10 raised to the power minus 3 kg. So that's in grams, 7.5 grams. And that contains that many free electrons, that is 8.2 times of 10 raised to the power 22 number of electrons. Let's move to the next page to see the rest of the question. The rest of the question has that how many electrons must be removed from that 8.2 times of 10 raised to the power 22 that was available to us. So that many free electrons, from that how many need to be removed from each of those two spheres, considering two such spheres, so that the electrostatic force of repulsion between them is just balanced by the force of gravitational attraction between them. Now the masses are given, the mass of each sphere is given, that is 7.5 grams if you remember, and they have a volume, and from that volume you can make out the distance between them. Now assume the distance between the spheres is great enough so that the charge on them can be treated as a point charge. So the distance, radius here, I don't know if the volume was effective or of any use. So let's see what we have at hand. So this is the 38th one in that series. So we have a metal sphere, we have a volume of 10 raised to the power minus 6. We will take care of that volume later. So this is a metal sphere, and each we'll be having two such spheres. Each sphere has a mass of 7.5 grams, which is 7.5 times of 10 raised to the power minus 3 kgs, and they contain 8.2 times of 10 raised to the power 22 free electrons, out of which some electrons have to be removed. Now we'll consider two such spheres, and the distance is going to be so big that they will be mere point charges, or the charge in them will be mere point charge. Now the electrons have to be removed, so each of them is going to acquire a positive charge, and the same number of electrons will be removed from each of those spheres, so same value of positive charge that they are going to acquire. And this repulsive force that they will be applying, the electrostatic repulsive force, that will be counterbalanced by the gravitational force between them. Now the gravitational force between them is equal to G, that is the gravitational force constant, times of m1 m2 over r squared, and that is going to be balanced by the electrostatic force of repulsion, which is k q1 q2 over r squared. In this case q1 is equal to q2, so k q squared over r squared, and similar case with the masses being the same, g m squared over r squared. And as you can see, if we take the ratio of this, then obviously they are going to balance each other, so the ratio is going to be 1. Then you have the values of g m squared over r squared divided by k q squared over r squared, and they are going to cancel out each other to some extent. We wish to know that q, from that q will be getting that what the number of electrons that will be removed by taking the case of quantization. Now in this case you have q square to be equal to, now g is equal to 6.67 times of 10 raised to the power minus 11. If you remember, 6.67 again is 20 over 3. You can take this take that as 20 over 3 times of 10 raised to the power minus 11. Remember I said that 0.67, well, you can take it as 2 over 3. So this is 10 raised to the power minus 11. Let me write that clearly for you. And then you have m in each case to be equal to 7.5. So 7.5 times of 7.5, no need multiplying that because we will be eventually taking the root over. And then 10 to the power minus 3, of course, minus 6, we can multiply that. So divided by 9 times of 10 raised to the power 9. Q will be therefore equal to the root over of this. Now let's check the power terms first. So this is minus 11 minus 6, so that is minus 17, and this 9 goes up, that becomes minus 9, so that evens out the power term, that is 10 to the power minus 26, and that under root is going to give us 10 raised to the power minus 13, the value. Now with that available to us, what we will be seeing are the rest of the terms. Now 7.5, two terms are there, so under root, if that is taken, you will be left with 7.5. Then you have 20 over 3 times of 9, so this is 20 over 27. Now for that, you end up with is that 2 over 3 is going to be root 5 over, well, that is you're going to have one of the 3's over there, and this is 7.5, of course, 10 raised to the power minus 13. 5 over 3 is, as you know, is 1.67, which is nearly equal to 1.69. So 1.69 is the square of actually 1.3, because 169 is the square of 13. So this is 2 over 3 times of, nearly we can take it as 1.3, and then we have 7.5 times of 10 raised to the power minus 13. Now this is the value of Q, and that is equal to n times of E. So we have the value of n to be equal to 2 over 3 times of 1.3 times of 7.5 times of 10 raised to the power minus 13, entirely divided by E, that is 1.6 times of 10 raised to the power minus 19. Now if you calculate this 3 cancels out with 7.5 to give us 2.5. 2.5 times of 2 is 5. 5 times of 1.3 is 6.5. 6.5 divided by 1.6 is nearly going to be equal to 4. And as far as the power of the 10 are concerned, you will end up with 10 to the power 6. So this is the number of electrons that will be, and this is by sheer near about assumptions that I have made, that I have been making. Let's check whether it's coming out to be nearly correct or not. As you can see, the value over there is exactly the similar that I have obtained, that is 4 times of 10 raised to the power 6, and that is exactly by assumptions that I have made this near about thing. So there's no There is nothing new about it, because I've said that with higher numbers, higher powers of 10 and all that available, it's good to take a few assumptions, near about assumptions. The next one is probably a kinematics related problem that has been linked to electrostatics. An electron is projected along the positive x-axis with a velocity of 3 times of 10 raised to the power 6, and because that cannot be 3 times of 10 to the power 8, of course, and it goes 0.45 meters and then stops due to an external electric field. Obviously the electric field will be acting, will be attracting that electron. So the magnitude and the direction of the field, well, so there was an electron which was traveling along the positive x direction, is it? Yes, positive x direction, and was traveling happily at a speed of, say, initial speed 3 times of 10 raised to the power 6. Then it was stopped, so that means its velocity becomes 0 after it has traveled 0.45 meters. And why? Because an electric field was applied which started attracting it with an electrostatic force. Now this is a single electron with a mass of, the mass of the electron is 9.1 times of 10 raised to the power minus 31 kg, near about value of 9. So again we are going to use a near about case over here as well. So this electrostatic force of attraction due to the external field resulted in the negative acceleration, of course, and that negative acceleration can be determined from this, that is q, that is the charge of the electron, 1.6 times of 10 raised to the power minus 19, e, which was provided in order to stop it, that is to be determined actually, and divided by m. We'll probably not use this value as of now. We'll keep it to EE or QE over M, so that we can obtain that, we can use all those values at the last instance. Now what has been provided is that this negative acceleration has resulted in a change in velocity over the distance 0.45. So S is equal to V square minus U square over 2A. So that means we have S, that is 0.45, V square is 0 squared, minus, this is negative of course, divided minus u squared was 3 times of 10 raised to the power 6, that will be squared, divided by the acceleration which was negative, of course, that is equal to E times of E over M. Now in order to determine this E, we take it up and we now can obtain the value. The minus sign, that will cancel out with the upper minus sign. So this is 3 times of 3 times of 10 raised to the power 12 at the top, divided by 0.45 has come to the denominator. From the other side we have the value of E now, 1.6 times of 10 raised to the power minus 19. The M goes up, so that is 9.1 times of 10 raised to the power minus 31. We'll see whether we will take it as 9 or not. And then that's it. That's those are the values that we need to consider. This is 3 times of 3 is 9, 45. So this is, I can take it as 45 instead of 0.45, and I can take a 10 to the power minus 2 over here. 9 goes 5 times with 45. 5 multiplies with 1.6 to give 8. So this is 9.1 over 8, nearly 9 over 8. And as far as the powers of 10 are concerned, 10 raised to the power minus 19 in this case, and then you have minus 19 over here, so that cancels out, and then the 10 to the power 2 goes up. So you have 9 over 8 nearly is equal to 1.125. So we'll keep it to that, and this is 10 to the power 2 Newton per Coulomb. And in what direction? Obviously E was acting along the x-axis, because in that case it will be dragging the electron backward, so it's going to be along the positive x-axis. So that's the direction as far as as far as that of the electric field is concerned. I've probably missed out on a factor 2 over here, because this is v square minus u square over 2a. So there will be a 2 over here, and this will be divided by 2. So the result is going to be nearly equal to 0.56 nearly times of 10 raised to the power 2 Newton per coulomb. It's ideal to take it as 57 Newton per coulomb, because there will be 56 actually, but because we have left out a few points over there, the extended part, so it's nearly 57, and that is exactly the answer that we are getting over there. There exactly you see that is 57 Newton per coulomb. I missed out that 2 over there, so that caused that mistake. Now, as far as the next question is concerned, you have a charge of 16 nanocoulomb to be fixed at the origin of the coordinate, a second charge of unknown magnitude to be placed at the point 3, 0, that is on the x-axis, and a third charge at 6, 0, that is double the distance from the first at the origin. The third charge obviously has the value of 12 nanocoulomb. What is the magnitude of the unknown charge if the resultant at the point, resultant field that is, at the point 8, 0 is going to be 20.25, and that is going to be directed to the right, and the distances are obviously measured in meters. So let's see what we have. So there is a 16, there's a 12, and the in between charge, you do not know that. We have to determine a lot of things to be considered. Well, the good thing about this arrangement is that they are along the same line, so that won't be a problem. So you just have to add or subtract whatever you need. So first of all, we would see that what is the value of the electric field due to just these two charges that have been given. Now from 16, it is at a distance 8 meters, and from this 12, it is at a distance of 2, because from 6 this is at 8, so 8 minus 6 is 2. So for that, we have the net electric field due to these two charges to be equal to, in terms of the magnitude, because they are along the same direction, they will be pushing a positive charge, because both of them are positive themselves. So this is K nano, and 16 and 12 are going to get, 16 over 8 squared plus 12 over 2 squared is what we are going to get the resultant from that, and that is going to be 9 times of 10 to the power 9 for K and 10 to the power minus 9 for that nano. So all we are left with is simple number 9, and then we have 16 over 64 is 1 over 4, plus this is 12 over 4 is 3. This is actually 3.25. It's essential to keep it as 0.25, because I have a gut feeling that it will help us. So this is 3.25 times of 9 Newton per coulomb. It's obviously going to be less than, greater than 20.25. So how much greater? Well, 225 and 20. So this is 29.25 actually, if you calculate it. So that is the value, but this is 20. So that means there has to be a negative charge, so that the field due to that negative charge is in the opposite sense, which is reducing this by a factor of 9.25. 29.25 minus 20.25 is actually 9.25 in the other direction, which is provided by this negative charge, which is KQ over the distance now over from this 3 right up to 8 is 5 squared. So that means you are going to get Q to be equal to 9.25 times of 25 over 9 times of 10 to the power 9. So that nearly equates to, well, 9.25, 25 is 625. We'll keep the 25 over here, we'll take the 6 up. So 25 times of 9 is 225, 231 divided by 9 That would have been nearly 25, of course, but just for calculation's sake, this is a nanocoulomb, of course. So that's nearly equal to 25 point something, 25. Well, it is provided 25 only, so we better take it as 9.25 can be taken as nearly 9. So that approximation, I didn't do it, but they have done it, of course. Okay, so the next one, that is the penultimate one, that is the 41st question. You have a charge 400 microcoulomb and is at a distance of 12 meters from another charge of 100 minus 100 microcoulomb. The strength of the electric field at the point C, that is 5 meters from B and 13 meters from A. Well, if you look at those dimensions, 12, 5 and 13, obviously they are forming a right angle triangle. So A and B are at a 12-meter distance. You have the point C to be lying at a 5-meter distance from B. That means it will be at the tip of that triangle, right angle triangle, and from A it will be 13. So let's draw the diagram over here. So the 41st question has A 12 meters, B, from B it is at a distance of 5. So obviously this is from A, it will be 13 meters, which has been given. So this is forming a right angle triangle. So that is the question. Well, I forgot the question actually. Now the question says that you have to determine the electric field strength at the point C, which is at the tip of that triangle. And the charges present are 400 microcoulomb over at the point A, and then minus 100 microcoulomb at B. And the net field, well, the field due to this, it will be along this direction, in the downward direction. So from the point C, one of the field due to E minus 100 will be along this line, and E plus 400 will be along this line. So the resultant is going to be somewhere between them, of course, but what we need to know is the angle between these two vectors. Now the angle, as far as the dimensions are concerned, we can choose them. Let me choose another ink because we are going to get into something different over here. See, there's the angles are obviously going to be pretty tedious to work upon, but we can consider this case. Now this triangle probably has an angle theta over here. So this line, the horizontal line, is making an angle theta. Now if you look at this component of this case, so E minus 100, not minus 100, E 400 has a cosine component along this direction and a sine component exactly opposite. So this is E 400 sine theta, exactly opposite to E minus 100. The reason I do this because there is no other easier way to try this. So first up, we see which of them is greater, E 400 sine theta or E minus 100. So E 400, as you can see, is KQ1 Q2 over 13 KQ1 over 13 squared. Let's take Q1 as this one. So this is 9 times of 10 raised to the power 9. 400 micro means 4 times of 10 raised to the power minus 4, and then divided by 13 squared. So that is going to be E400. Sine theta in this case is going to be equal to the perpendicular over the hypotenuse, that is 5 over 13. So that means E400 sine theta is equal to 9 times of 10 to the power 9. We can take it as 10 to the power 5 because there is a 10 to the power minus 4 over there. Then we have 4, that divided by 13 squared. Then you have 5 over 13. So that eventually gives us 9 times of 20 is 180. 180, we keep 18 and we take the 10 with this, 10 to the power 6, and then we have 13 cube over here. As far as E minus 100 is concerned, we have that to be equal to 9 times of 10 raised to the power 9 times of 100 micro means 10 to the power minus 4 divided by the distance, in that case is just 5 squared. So by the look of it, what we can say is this is 9 times of 10 to the power 5. From the look of it, we can easily predict that E minus 100 is actually going to be greater. And how much greater? We can find out the net electric field along the y direction that we see. Let's take this as the y-axis. So this is along the y direction. What we get is 9 times of 10 to the power 5. We can take that as the common term. So we are left with only 20 over here. 20 over 13 cube, 1 over 5 squared minus 20 over 13 cube is the value that we are going to get over here. That looks unfamiliar. We'll prefer keeping it like that. Looks pretty tedious as of now. We'll see if we can simplify that. Then we have E400 cosine theta, and that is acting along the x direction, so that is equal to 9 times of 10 to the power 9 for E400, and that is 4 times of 10 to the power minus 4 divided by 13 squared again, and then you have for cosine theta you have the value of base, the base divided by the hypotenuse, that is 12 over 13. So again you are going to get 9 times of 10, 9 times of 4 times of 10 to the power 5, and then you have 13 cube below and a 12 extra over here. So this is along the x direction and or the horizontal line, and that is along the y direction. So resultant is going to be the square of these two terms taken under root, which if done, then what you are going to get is 9 into 10 to the power 5 is going to be the common term in each case. And as far as the rest of the terms is concerned, what we can get from them is that you are going to have the resultant net field to be equal to the magnitude of it, that is 9 times of 10 to the power 5 is going to be the common factor in each of those cases. And then you have the values to be something like this. They may look pretty difficult, but the numbers are such that you have to calculate them all by yourself. So this is 13 cube, this is 4 times of 12, 48 over 13 cube squared, plus 1 over 5 squared minus 20 over 13 cube squared, all under root, so that is to the power minus to the power half. Now I give it to you to calculate this, because I won't really calculate these things because I won't be using the calculators for sure. So you can try this with your calculators, or probably come up with a shortcut method and give it to me so that we can share it and learn from that. So I would put it on you to find, because we have done so many easier methods earlier, so probably you can come up with something easier to calculate this kind of value with the data that has been provided to us, because the angles obviously won't be the familiar angles of 30 degrees or 45 degrees or even 60 degrees or something like that. So all that you have is theta and the dimensions that are available to us. So from that, if you are coming out with something easier to calculate this, then let me know. I'll definitely share that along with your name or in any of your or with your channel, probably, if you have any. I'll be happy to do that. Now as far as the 42nd number is concerned, I won't be doing that, because that's more efficiently done by using the Gauss theorem than any other method that is available to us. So I'll leave it right there. I'll do up to 41. I'll leave the 42nd bit because uh, will be I've done that in the theory part in the while discussing the Gauss theorem, or the theory related to the electric field. You can check that for yourself. So we'll leave it up to here, and so we have done almost all the questions that were provided to us. And let me know if you find something difficult or probably couldn't understand anything, probably in the comment section, so that I can clarify that. And if you need some other video related to some concept, do let me know. We'll try that for sure. Till then, thank you for watching.